Hello! Here is a screencast that I hope actually works this time. We'll see if you can actually read them. Look, I think your easiest strategy is to go into the week 21 folder and go ahead and print off this center of mass unit notes and go ahead and print off the momentum unit notes too. So if you go into the week 21 folder, you'll see what I'm talking about. Print them both off. It's way easier when they're printed. So you go ahead and push pause and then print those. And then when you come back, I'll be waiting right here. So push pause now. Hey, welcome back. Look, when we're talking about center of mass, we're talking about the average location of where we can consider an entire uniform or non-uniform body's average most midpoint theorem location of mass, if you want to use a statistic term. It's great when we have something like, you see the guy doing the hammer. Well, the center of mass for this ball would literally be, and I don't know why my screen is advancing. That's kind of crazy. That's not letting me write on it. It's kind of making me mad. Let me see if I can get this fixed here. Let's see if red's a winner. Red's a winner. Here is the center of mass of the guy. That's the average location of all of his mass particles. The center of mass for this is dead center of a ball. And that makes sense that if you take something like a sphere, that the average location in from the edges is dead middle. Any way you want to look at it three-dimensionally, the center of mass of a ball, if you're dead center, you're equidistant from the exterior. So we can look at the center of mass of the hammer. We can look at the center of mass of the dude doing the hammer. Or we can go with a new idea, which is called the center of mass of the system. So that would be the center of mass of the system. And you'll always see COM used as an abbreviation for center of mass because who wants to spell that thing out each and every time? Now, don't write this down on your notes. This is just for practical purposes, okay? This is just a reasonable explanation for what that special point is, the center of mass. And I want you to consider going into the weight room. If you go into the weight room, you've got them really funky looking barbells. Those really funky looking barbells have the bulk of the mass on the ends. So this could be like M1, that'd be like M2. And then there's this magic sweet spot that you put in your hand so that it's balanced. Well, that place is called center of mass, okay? Now, our book calls it COM. This old book just called it CM. So you'll see it both ways. I don't care which way you use it, but that's what that means. Now, if we want to look at it on a grid, this is the picture that's in the upper right-hand corner of your unit notes. The most important thing to remember when you solve these problems is that you have to pick an origin. And that origin is how you are going to analyze these problems. Origin. Almost wrote original. Origin again. So if we're going to figure out what the center of mass is for things that have equal masses, well, that's easy. The center of mass is right in the center. That's easy. But what if we want to consider the center of mass for something that's larger? Whoa, we got a big mass there and a little mass there. Well, there is the dead middle, but we can see that the center of mass has shifted itself over towards the larger object, kind of like the picture we had on the first slide of the athlete swinging the hand. All right. What about a cylinder? Center of mass is dead middle. What about a flat piece of paper that we cut out into a hexagon? Center of mass is in the middle of this. Piece of cardboard cutout. What do you want me to write down then, Matthew, in my unit notes? Well, if we're talking about the center of mass as being the weighted average position of the particles in the system, then we also can use an equation to solve this out. So in one dimension, this is what you want to write in your box right here, Ashima. You want to write that in the x dimension, which is right here, I can find the center of mass for any object if I know this mass and I know this mass, and I can calculate where they are according to an origin. Now look, this one's at x equals 0. This other one is at x equals 2. So you can see that if I wanted to put in the center of mass for this, I would say that M1 is on the origin, and that M2 is maybe a mass of 1 kilogram at a distance of 1. There's no other additional pieces of information, and then I would have to divide it by the number 2. If I did that, then my x location for the center of mass is 1/2. And look, that lines up with 1/2, especially if we denoted x2 as 1. So you don't have to write down any of that stuff that I just did there. I'm just showing you that for illustration purposes. It's really helpful if you just write down this equation. And that equation is super duper useful. Look, all you've got to do, if you want to find the x in the center of mass, in the x dimension, we have that equation. Oh, by the way, I already gave you this on your sheet. This is already done for you. You don't have to write this. You can just look at it. If you want to find it for the y, substitute in for the y. You want to find it for the z dimension, substitute it in for the z. What is that useful for, you might ask? Well, if you're doing GPS devices, we pick an origin, and then we come an I hat this way, maybe a K hat this way, a J hat this way, and you could locate this little sphere-y looking ball. You can locate that anywhere you want in three-dimensional space, provided you have an origin that you started at. And once again, just like in vectors, the origin really matters when we're doing this. All right, and that's why we see radial vector CM is comprised of I hat, J hat, and K hat mentality. So what does that mean for me, Mr. Matthew, if I'm solving a problem? Well, consider the following problem where you have a mass 1, a mass 2, and a mass 3 on some type of a grid, okay? So let's just say that I have a grid where I have an established origin right here in the center. Well, then I can put mass 1 at 3, and then, that K, see, 3 in the I is fine, but we have to have that K hat come out of the screen right here. But that's what that means. And then we would put a mass there, kind of out here in free space, coming at us. The next mass, we would put -4, 2, and then it would have to come out in free space. And then the other one would be 10, way over here, so you get what I mean. But once we have all those coordinates down, then the easy part comes. Now, I would like you to simply take a screenshot of this if you want. Like in class, we didn't do these calculations. Man, if you can do one of them, and if you're not doing screenshots, that's fine. All I want you to understand is that if I want to know what the summation is in the x dimension of that center of mass, and that's what that means. That's a statistic symbol. It's to say sum up all numbers where you're starting with the first one. You just put down this mass and this x dimension. The next mass and its x dimension. Then you put down, this mass and its x dimension. And then you just calculate. And then you do the same for the y, you do the same for the z, and then you come up with the center of mass point for this system with all these varied masses. And you write it down as a collective answer. So that's pretty simple. What happens if you have an object that isn't regularly shaped? Like you've got this big space rock, and you want to figure out where its center of mass is. Well, we can actually use integration to help us out. So on your paper, what I want you to put is above the box, because you have a box where you're eventually going to put this. You're going to put this in the box on your paper, there on the left, halfway down. But before we even get to that, I want you to consider the following. What if I have a cone, and that cone has an infinite number of mass particles? I can put these dots until I can't even think straight. I can put those dots for infinity, right? There's all these little mass dots. Well, how do I know where the centermost one is? Well, simple. Step one. We would add up every single mass point and every single distance x from an origin. If you added them all up, you would get a center of mass. Well, it'd take you forever, and you have to divide it by the total mass. It'd take you forever, but you could do it. Well, that isn't very practical. What's another way to do it? Simple. Instead of using a sigma, let's use an integral, and we'll find all integral values of x as a position compared to very, very small pieces of mass. So as long as we have a function where dm is a small element of the mass and x is the x-coordinate of that element, we're really doing the same thing as we did before in that equation, but now we're going to use calculus to help us shortcut this idea right here. All right, and what would that idea look like at the end of the day? I did not go into this today because this is a little more complicated, and I want to do this with you guys sitting in seats. So ignore this, Ashima. Ignore that. Don't even write that down in your box. I can see you getting ready to write it down. I want you to abandon ship. I want you to abandon ship, and I want you to go to the new sheet that you printed out, which is on momentum. So we start the idea of how we can talk about momentum as far as center of mass goes. And then we move ourselves into the actual act of momentum here in AP Physics C. And I got to tell you, this actually ends up being one of the easier units for everybody. And the reason why it's one of the easier units for everybody, sorry, I'm walking around the room. So you're going to want to flip it to your new page that says Unit 9, Part 2, Momentum Defined. So you see at the top of that sheet there. Look, you know what I like about momentum, Ashima? There's literally, well, I'll tell you, every time I use my green marker, it's freaking out. It makes my screen advance. So I'm going to use red. The thing that most people like about momentum is not that golf is just cool. What most people like about momentum is there's literally two equations to have to remember. Momentum equals mass times velocity, and force multiplied by time equals mass by a change in velocity. There, I can do everything in momentum if I have these two things memorized, down pat, understood, like the back of my hand. So why do we have this big unit note sheet then, Matthew? Well, because putting them together takes a little bit of patience. So what I'd like you to put down underneath where it says momentum defined, I want you to put this little box, and don't make it giant in there. Put that box down and say momentum, vectorial momentum equals mass times a velocity vector. That's our equation we start off with. And then underneath that, I think you can really just put momentum as a vector, and the SI units are kilograms meters per second. That's all you need to put down in Roman numeral 1, momentum defined. So for Roman numeral 1, momentum defined, you're going to put down that equation, and then you literally have two boxes, and you can write everything super small. You're going to go on your sheet to Roman numeral 2. which says time rate change. Well, Isaac Newton knew that in order for people to clearly understand what he's talking about, he needs to come up with a clean way to describe this idea of his. So, he did a really nice job. Check this out. Force equals mass times acceleration, right? Well, look what he did. Force equals mass times acceleration. So therefore, force equals mass times a change in velocity over time. Therefore, mass equals a change in momentum over a change in time in very small parts. Bam! The whole unit is done. The whole unit is complete. All we have to remember, Ashima, is that a force changes momentum, and if momentum is changed, it's because a force did it. That is so powerful, it drives everything that we do in physics, is understanding this one simple idea. So that is how we define what is exactly going on, okay? So what do we mean by Newton's second law drives physics? For Newton's second law, up in the right-hand corner, I believe it's Roman numeral 3, I just want you to understand the flow of how this idea works. If force equals a mass times acceleration, look, I just wrote out what I jumped the gun. There. It's really the same thing I just did over there. I forgot that we had a spot for it. Okay? I know you're really good at calculus, so what I do need you to understand is that since force equals this idea of momentum, then I can go back and integrate it. Like, I can take the standalone idea, I can multiply time by both sides, and if I get this idea, I can integrate both sides of this. And by integrating both sides of that for a time constraint, I've actually developed the idea of final momentum minus initial momentum equals force multiplied by time. He came up single-handedly with the idea that if I want something to move, look, here's just a random box on a table. If it's not moving, it doesn't have momentum. It has mass, but its velocity equals 0. Isaac Newton said, you want to know how you can move something? Apply a force over a time period. That's called an impulse. An impulse will give this momentum. Well, what if something is already moving, Mr. Matthew? What if something is moving this way? How do you stop something? Simple. That's a velocity, by the way. How do you stop something? You apply an opposing force, and you do it for a time period. That's called impulse. So what is impulse? Give me the lowdown on what impulse really is. Impulse is just a description of this side of the equation. An impulse is force multiplied by time. What does an impulse cause? A change in momentum. Not just momentum, you have to have the triangle where you don't have an impulse. The author of your book and all AP Physics books use this J to represent impulse. Matthew, why don't they just write an I, bro? I is also used in electronics to represent current, so they had to use a J because it looks like an I, but it's not an I. That's just what they use. Okay? So what do I need to know about impulse that's really cool? Well, it's a vector. And graphically, it's literally the area of a force time graph. So what is impulse? Impulse is the area of an F versus T graph. An F net versus T graph. I shade in this area, it's an impulse. Unfortunately, my graph is all jacked up. It should be just 2. Should be just 2. I don't know why that yellow got up, but if I go 2 and 4, that gives me 8 Newton seconds of impulse by shading it in. And you know how to do that. That's simple. We did that with work. You know, if we shaded in a force to a change in x, this is work in joules. Okay? If we do it now with time, it becomes an impulse. Well, Mr. Matthew, what if that curve isn't a straight line? What if it's not geometric? Well, if it's not geometric, we can use upper and lower sums. And this is how Newton got onto the idea of integrals. He thought, look, if I can just take something that's curved and I can, in geometry, take upper and lower sums and cut this part out that's outside and put it over here, cut this part out, put it in here, cut this part out, put it in here, cut this part out. And if you just keep doing that, it all balances out. So, in a way, every single one of these members becomes something that integrates into what would be the total amount of impulse. So that's why we can use an integral to make that happen. And those integrals, when we get them in AP Physics, they're always really simple. You know, they don't tend to have a bunch of crazy exponents, logarithms, what have you. Okay, I just want you to write this down now. I'm not going to talk about relationship 7, logic behind collisions. Forget about it. It's just easier to write down in Roman numeral 8 box. Conservation of momentum. I want you to write that down. What can you write down as a statement? Momentum is always conserved. That's what I would write down in the open space. Momentum is always conserved. And then in the box where it wants the equation, here's your equation. There it is. There's your equation. The momentum, the sum of the momentum before equals the sum of the momentum afterwards. So look, it looks like a really difficult equation, but in reality, momentum plus momentum equals momentum plus momentum. All of the momentum initial equals all of the momentum final, regardless of how many members there are. You could have M1, M2, M3, M4, doesn't matter. Okay, so that's pretty cool. When it comes to collisions, there's 2 types. And elastic means that things literally bounce off each other. So there says 2 equations in those box. Ashima, I don't want you to put this down. In the second box, forget the second equation. Just know that this is an elastic collision. And that means that energy is usually conserved, but not all the time. Momentum is always conserved. All right? What does an elastic collision look like? Well, a rubber ball bouncing off a wall, pool balls bouncing off of each other. Mr. Matthew, if this is a collision that you say is elastic, then what would you consider to be inelastic? And inelastic, skip the section on relative velocities too. There's no payoff to it. Look, when we're talking about things that stick together, catching a football, catching a baseball with a glove, a dart going into a dartboard, a car crashing into another car and they stick together, a comet hitting planet Earth, that would be a collision that is inelastic. Or they could have just said not elastic, but they used the word inelastic. Unelastic. That means the momentum of A plus the momentum of B equals the combination of A and B. So we just combine their masses. But in reality, Ashima, I need you to know the momentum of 1 plus the momentum of 2 equals the momentum of these guys in a new configuration. So I'm not inventing equations here. I'm using the same equations. I'm just using them creatively. So before, these items are on their own. They've got their own velocities, they've got their own little lives. Afterwards, they're stuck together. Well, we can flip that around so that they're stuck together beforehand. So check it out. They're stuck together beforehand, and now they go about their own little lives. And that is called an inelastic collision, run in reverse. Some books call it the explosion equation. It's literally just the reverse of an inelastic collision. Man, I know that was a track meet, but that's exactly what we did in class today. Rewind it if you need to hear some more stuff, but that's all the further we got in No Journal today. So I hope it all makes sense to you. And that's it.